Some time ago I was browsing the Stack Exchange electrical engineering site and this question got my attention. Weird? An assortment of circuits and charts were been displayed. It really sounded weird. But what really caught my attention was the circuit presented by one of the fellows answering the question. It was a copy of the electronic circuit breaker I have presented in one of my YouTube videos. What was most striking was the explanation presented on how the circuit might have its origin. A monostable multivibrator. Really? The fellow even go to the detail of describing the functioning of the multivibrator as it applied to the weird current protection circuit in discussion. To erase any misunderstanding, I have done this video where I describe in detail how the circuit in my videos work. So let's start with it.
Current limiting circuits. How efficient are they? Current limiting circuits perform their work by dumping the excess energy created by an increase in the load current into the control circuit, usually into the series pass transistor. This results in an increase in the thermal condition of the circuit, with the potential for damage if proper heat sinking devices are not used. This document provides an alternate design to limit load current without the need for heat sinking devices. It also provides a solution for short circuit conditions not addressed by the usual limiting circuits. Most current limiting circuits are simple like this one. A resistor, R1, is sized to drop 0.7 volts when the load current is at its maximum. This triggers a transistor, Q1, to divert the base current from the series pass transistor, Q2. The result is the reduction of the current on the pass transistor, Q2. In doing so, the pass transistor comes off its saturation state, where VCE is very low, around 0.3 volts, and consequently its power dissipation is also low. The resulting increase in VCE requires high-power transistors and/or large heat-sinking devices, increasing complexity and bulk of the circuit. Most important, these circuits do not block the current for cases of short circuit as fuses do. But fuses do not come in small values, and need to be replaced when blown.
Let's go over some of the values for this circuit. Here we can see that to limit the current at 650 mA the power dissipated on the transistor can go up to 7 watts. That is why a heatsink is needed, to dissipate the extra 6.5 watts. Of course we are assuming that the LED is a high power LED, possible of been driven up to 1 amp and 1 watt. What if we replace the LED by a generic resistive load, where we can change its current by reducing its resistance? Here is the circuit with the two NPN transistors with a spec of 800 mA and 500 mW. As explained in the video, the current going through the load and Q2 is controlled by the 1 ohm resistor R1, which will turn Q1 on once the maximum current is achieved. And here is the simulation. Current limit of 660 mA and power dissipation of 8 watts. The difference here, from the previous LED circuit, is that in the previous circuit we altered the power supply. In this circuit we maintain the power supply voltage and change the resistance of R1 by varying the X variable representing R1 resistance. This is achieved by the dot step param varying the value of X from 500 to 0.1 in steps of -1. By adding another plot pane we can see how the circuit leave its saturation state, causing all the voltage from the power source to fall on Q2. This is what is causing all the 8 watts power to be dissipated on Q2. Until then, the power dissipated was very low, which the transistor could handle.
So what to do when you need 1. A simple circuit with the least amount of discrete components. 2. That dissipates very little heat so does not need heat sinking devices. 3. Prevents the load current from going above a certain limit. 4. And if it does, like in a short circuit situation, it shuts down the pass transistor. 5. And it can be restored to normal operation when the high current condition disappears. There is a very simple solution to resolve this. 1. Eliminate the sensing resistor. 2. Use the pass transistor VCE as the limiting sensor. And here is the circuit. The circuit works by using Q1 SVCE equals 0.7 volts to trigger the current limit. This turns Q2 on end. As a result, turns Q1 off by grounding the base of Q1. This means that Q2 needs to run saturated, so its VCE is below 0.7 volts, cutting Q1 off. The optional circuit turns LED 1 on to indicate the circuit has been triggered. Resistor R1 needs to be sized to saturate Q2. I have used 1K. And resistor R2 enough to light LED 1. Also 1K. Capacitor C1 is needed to keep the circuit stable. I have used 1 microfarad 50 volts. Removing the high current condition and resetting the power resets the circuit.
But how did we get here? Remember this circuit? How about if we make some changes to it? Move R1 to between the collector of Q2 and the base of Q1. But we need to change the values of resistors R1 and R2 so we have the transistors running saturated. And connect the emitter of Q2 to ground. Here we have an electronic circuit breaker that will shut down when the current reaches a certain limit. In this case 150 milliamps. And a power dissipation of only 80 milliwatts. When Q2 goes out of saturation, the circuit triggers. This is caused by the voltage between the base and emitter of Q1, raising above a certain threshold. Look how the base of Q1 has been below 0.7 volts, until it raises to 0.87 volts. What happens if we change the value of R2 from 10K to 20K? The current limit changes to 88 milliamps. What if we change the transistor type? It changes as well. But the power dissipated is still below the transistor's maximum dissipation. If you check transistor's maximum current and maximum dissipation, you will find out that these values, usually, apply when the transistor is saturated. That is, with a low VCE.
You will need to do some experimentation to find out the right value for RV.
In part 2 of these series of videos we improve in the design of the circuit to account for a possible shortening of the load to ground.
Part 2. In my last video, I have shown how a current limiting circuit could be built without the need for heat sinking devices and or sensor resistor. The circuit used two NPN transistors. One as a current pass transistor, the other as a trigger transistor. The circuit uses the pass transistor collector emitter voltage, VCE, to trigger the current limit. When this happens, the LED turns on, indicating the circuit has triggered, and the current and voltage drop to almost zero. Indeed, what I have built is an electronic circuit breaker. An electronic fuse, if you wish, that could be used with low current circuits. Here is the circuit. How it works was explained in my previous video. One of the characteristics of this NPN transistor configuration is that the supply positive voltage is the common rail. The DC input ground is separated from the load ground. The pass transistor Q1 is configured as a sinking device. But why does it matter? It matters because, although the circuit is designed to trigger when the load short circuits, it will not trigger if the load positive is shorted to the input ground.
Let's review this. Here is what happens when we short circuit the load to ground. The current bypasses Q2 and goes straight through. But back to the video.
To make the ground as the common rail, we use PNP transistors instead. To do that we change the polarities of the DC input. and change the transistors from NPN to PNP. But let's make the drawing more user-friendly, with the positive on the top, and the negative ground on the bottom. I have also eliminated the capacitor, as the circuit was more stable and did not need it. The pass transistor Q1 is now a source device.
Let's see how the circuit will now behave. Changing the NPN transistor to a PNP and inverting the power supply poles. This is what we get. But of course, the charts are now inverted, so we change their signs. Notice that the red plot is the power dissipation of the load, not the transistor. For the transistor we draw the green chart. Again, it is inverted, so we change the sign. The current and power are different because we have not provided a specific transistor model. Remember that the load and transistor power dissipation will be proportional to the current through it and the voltage applied to it. But back to the video.
Conclusion. The new design of utilizing PNP transistors result that a short circuit to the common ground will cut off the power to the load, the breadboard attachment pins, and the jumper configuration for RB provide a way to work with several different current limits when performing breadboard circuit tests. Stay tuned. Part 3 is coming up with new additions to the circuit. Current limiting circuits. Part 3. In the first video of this series, current limiting circuit breaker, I present an alternate design to limit current in a circuit and protect it against short circuit by removing the sensor resistor and using the pass transistor collector emitter voltage VCE instead. Heat sinking devices are no longer required. The circuit uses the pass transistor collector emitter voltage VCE to trigger the current limit. When this happens, the LED turns on, indicating the circuit has triggered and the current and voltage drop to almost zero. What you see once the circuit triggers is the LED current and voltage. The circuit used two NPN transistors. One is a current pass transistor Q1. The other is a trigger transistor Q2. Here is the circuit. How it works was explained in the video. You will find its link in the description. In the second video, Electronic Circuit Breaker Part 2, I improved in the previous design by replacing the NPN transistors with PNP transistors. By using PNP transistors, the circuit changed from a sinking to a sourcing configuration, making the ground the common rail, improving its short circuit capabilities. Here is the circuit. How it works was explained in the video. You will find its link in the description. I also added pins for shorting jumpers in place of the past transistor base resistor to limit at different current levels. Here is the RB resistor replaced by pins for shorting jumpers and resistors. RB110K resistor, RB250K resistor, and RB3 also 10K resistor. But I am not happy that different power supplies and transistors with different current gain using the same base resistor can change the current limit. Quote from the second video. It needs to be said that the current level is not only dependent on the Q1 pass transistor gain characteristics, but also the power supply voltage. In this video I make an improvement. The sensor resistor is back.
I thought I would never see you again. That you are out of my life.
Wait, it is not what you are thinking.
I don't know what's right any longer. You have to think for both of us. For all of us.
I am still protecting against short circuits. No need for heat sinking. And still using the collector emitter voltage to trigger the circuit. Here is the original circuit using Q1 0.7 volts as a current limit. By introducing back the sensor resistor in series with the collector emitter voltage to trigger the circuit, I don't depend on the transistor gain and or power supply voltage. The new design uses the collector emitter saturation voltage, usually around 0.3 volts, plus a drop of 0.4 volts on the sensor resistor, for a total of 0.7 volts to trigger the circuit. I added the sensor resistor between the collector of the pass transistor Q1 and the base of the trigger transistor Q2. Here is the new circuit using Q1 0.3 volts VCE saturation voltage, plus RT sensor resistor 0.4 volts drop voltage as a current limit. For the difference of 0.4 volts, I use the sensor resistor with the following formula. Current limit equals 0.4 volts divided by the resistor value.
Here a sense resistor of 1 ohm gives a current limit of 400 milliamps, with the VCE contributing 250 millivolts, resulting in a VBE on of 650 millivolts to trigger transistor Q2. Here is the circuit built with a current limit of 500 milliamps using 1 ohm sense resistor. To trigger the circuit when the 500 milliamps current is reached, we have to increase the base current. The reason for that is because the transistor has to run saturated, which means a ratio of collector to base current of no more than 20:1. By changing the base resistor to 500 ohms, the base current changes from 12 milliamps to 24 milliamps, red line in the chart, allowing us to run the circuit up to 480 milliamps before the circuit triggers, ratio of 20:1. With a 1 ohm sense resistor, the circuit triggers with a collector to emitter voltage of 300 millivolts, green line in the picture, and trigger transistor Q2 turns on at around 700 millivolts, cyan line in the picture. In this circuit, I have replaced the capacitor C1 with a switch. This not only allows me to reset the circuit when it triggers, without disconnecting the power supply, but also to account for inrush current. As the simulation shows, without the capacitor between Q2 emitter and base, the circuit is initially off, cyan line between 0 and 10 seconds, allowing the inrush capacitor, or other type of inrush circuit, to stabilize. When the switch is activated at 10 seconds, the circuit turns on, only shutting off when the current exceeds 480 milliamps. To summarize, Part 1 presented a new current limit design that works as a circuit breaker, avoiding the need for a heat sink. Part 2 improved the safety of the design by replacing the NPN transistor with PNP transistors and added pins to attach the circuit to a breadboard while performing tests. Part 3 brought back the sense resistor to control the current limit, instead of using the base current and transistor beta gain to determine the collector current. The new design uses the VCE plus sense resistor voltage drop to target the collector current and corresponding load current limit.
Conclusion. The new design of utilizing the combination of the pass transistor VCE saturation voltage and the sensor resistor drop voltage provides a more accurate current limit. It does not depend on the pass transistor current gain or the power supply voltage, and it will still maintain the original circuit objectives. Shutdown if a short circuit occurs. No heat sinking device. Current limit by resistor, not base current. Current limit not dependent on power supply.
And that's all, folks. I hope you enjoyed the video. And I thank you all for watching. Thank you.